I'm gonna wait until we get our first viewer in here before we go ahead and get started talking. So just hang tight. Awesome, looks like we got a couple viewers in here. So hello everybody, welcome to another 1 o'clock demo here with Arizona Science Center. And today, it's gonna be one of my personal favorite demos here. We are taking you through the science of hockey and some of the different things that happen in one of my absolute favorite sports, hockey. Now, one big concept that plays itself out a lot in just about everything that has to do with hockey is the concept of friction, as well as the concept of energy transfer. Now, friction is basically the force of things that are rubbing up against each other. So in hockey, you get a lot of that with the ice skates, right? When they're on the ice, with the puck sliding across the ice. And there's a lot of different things that involve friction. And without friction, a hockey puck would just keep going along the ice and it would never stop. You need that friction to slow it down. So we've got a couple cool demos here to show you how friction impacts hockey. And the first thing I want to do, I'll be right back. The first thing I want to do is show you exactly how an ice skate works. Now I've got this ice skate right here. It's specifically a hockey skate. So there's a few different types of skates that are out there. You've got hockey skates, you've got figure skates, and you've got like speed skates. Now, with hockey, the blade, a lot of people don't realize this, but on a hockey blade, it actually has two edges. A lot of people think it just comes to a point and it just digs right into the ice. But if you see, the blade has two edges. It's got this edge, an inside edge and an outside edge. Now, with a hockey skate, one of my favorite kind of parts of it, it's kind of hard to see, so we're going to see how close we can get, but it's actually concave in the middle. So you've got the edge, and then it dips down a little bit, and then you have the other edge. And the reason behind that is to actually somewhat increase the friction. It increases the grip. So with the two edges and a little bit of a gap in between, when it digs into the ice, the edges will cut in, giving you much more grip, because a hockey player is going to need a lot more grip compared to like a speed skater, which a speed skater skate is actually completely flat on the bottom because it needs to be able to glide across the top and reduce that friction. So hockey skates, different skates have a different amount of curve depending on how much grip you want. So if you have less curve, you're gonna be able to go faster because it reduces the amount of friction, but you might not be able to stop as well. And when a hockey skate is stopping, when you see a hockey stop, what's happening is the skate tilts to the side, right? And that inside edge, so when somebody's stopping, you get that inside edge. The inside edge is actually shaving that top layer of ice off as it glides, which is why you see all that snow kick up whenever a hockey player is stopping. And you get that inside edge, cutting it off, increasing the friction until finally the friction on this side stops it to the point where it completely brings the player to a stop. And there's a lot of different mental calculations that are going on while a player is doing that, depending on how fast they're going. But another cool way to talk about friction is with the pucks themselves. Now, we have a couple kind of makeshift pucks here, but they all have a special little trait to them. Now, each one has a number. They're all exactly the same weight, but they have one big difference, and that's the bottom. Now, I'll go in order here just so we don't, get too far out of order. But this is our puck number 1. And the bottom has this kind of foam, kind of felty bottom. So it's smooth, but it's got a little bit of grip as I rub my finger across that. So we'll remember that. I'm going to put it down here. Now, 2 has more of a cloth bottom. So very, very soft, but still a lot of kind of grip to it. Puck number 3 here has a very smooth bottom. This is basically just straight, like kind of like a plastic bottom. So it's very, very smooth. And puck number 4 here has a very rough bottom. This is sandpaper if you need a point of reference. This is sandpaper, very, very rough. Now, a hockey puck itself, a real hockey puck, is going to be like this. Very smooth. It's got some grip on the edges, but on the bottom, the parts that are going to be on the ice the most are going to be very, very smooth. Now we're going to see, and I'm going to try to do this. Now, one thing to remember while we do this isn't perfectly scientifically accurate because I can't guarantee that I'm applying the same exact amount of force every time, but I'm going to try as close as I possibly can to apply the same amount of force to each of these pucks, but we're going to try to slide it across our surface. And I'll show you this surface. We got 3 different zones. This right here, very smooth, nothing on it, most similar to what an ice rink would be. This is just one layer of the same type of tape, kind of in strands, a little bit rough. This one is similar, but a different type of tape and smoothed down a little bit. And we're gonna see how the different pucks react to sliding across this. And the only real difference is gonna be the surface, which is gonna change the amount of friction that's applied. So I'm gonna angle the camera down a little bit so we can hopefully see this a little bit better. And we're gonna try this out. Now, like I said, I can't guarantee that I'm applying the same amount of force, so if I had some type of mechanism to do this, where I could guarantee that I was applying the same amount of force, we could guarantee that we would be getting perfectly accurate results. But this is our first one, puck number 1 with kind of the foam bottom. So, cool. So with about that same amount of force, it's getting maybe halfway on our ice, right? So let's try number 2. 2 is gonna be with our cloth bottom. All right, so about that same amount of force. It's going a pretty similar distance. Okay, cool. So number 3 is gonna be our smoothest bottom. This is gonna be the most similar to what an actual hockey puck is. Now these are different experiments you could try at home. You could try it with different materials on different surfaces to see what would have the most friction, what would have the least friction. Now this is most similar to what our hockey puck is on what's most similar to what our hockey rink is. So with the same amount of force, it looks like it's sliding a little bit more. So it's going just a little bit further than halfway. And then this is our 4th one. This is the one that's very sandpapery. We're gonna try this out. And I promise you I'm trying as close as I can to apply the same amount of force. I'm gonna even try to apply more force here. And you'll see that it's barely sliding at all. And we're gonna try the same thing. We're just gonna do a couple of the pucks though. We're gonna try the same thing on zone 2. We're gonna start with our sandpaper puck since we already got it. You'll notice that with that increase in friction, this didn't move at all. It actually grabbed this so well that it moved the whole thing. So I literally can't slide this across this. Compared to, we'll go back to 3, which is most similar to our regular hockey puck. That'll slide across there very well. And that's because of that decrease in friction, right? So if you were designing a hockey puck, you probably wouldn't want a puck with a rough bottom because it wouldn't slide across that ice nearly as well. Now, ice itself is going to decrease the amount of friction, period, that anything is on there. So things are just going to typically slide better on ice anyway. But that's why they have that smooth design. Now, another cool thing that a lot of people don't know about hockey is in hockey, they typically will keep the pucks on ice. So all the extra pucks, they keep them on ice throughout the game. Now, the reasoning behind that is because this is made of vulcanized rubber, right? It's basically super condensed rubber. When it's colder, it's not gonna bounce as much. So the puck's gonna stay on the ice more. When they shoot it, it's not gonna be bouncing everywhere. It's just gonna kind of stay on the ice and glide. Compared to a warmer puck, the molecules are gonna be spread out a little bit more. It's gonna be much more bouncy. So I've got 3 different pucks here. This puck I had sitting outside all day. I know you can't tell, but it's really, really hot. This puck is normal. It's just been sitting kind of in the container over there all day, so this is kind of room temperature. And this puck I've had in the freezer for the last 5 hours, so this one is really cold. This is what would be most similar to an actual hockey puck on game day. So we're gonna test how high they bounce in relation to how hot or cold they are. So this first puck, this is our frozen puck. So we're gonna see how high this bounces. I'm gonna try to drop it as straight as possible. So you'll notice that that basically didn't bounce at all. That hit the ground and just stopped. It flipped right over. We're gonna try that again. Same thing, right? Now, there's other factors that can come into play, right? There's some factors depending on exactly where it lands that might impact how it bounces, but for the most part, that one barely bounced at all. Now, this puck right here, this is our puck that's been sitting outside all day. So we're gonna see how high this one bounces. Oh, So that was a really interesting one. So let's try it again. So you'll notice that this one seems to keep bouncing up and flipping over to its side. And it all depends on exactly where it lands, right? So again, like I said, this isn't perfectly accurate, but this is a fun one to try at home as well with other things, not even just hockey pucks. So we're gonna try this again. And you'll notice that that one had a little bit more bounce than that puck. Now this is our normal puck. And it had a little bit more bounce than the frozen one. But a little less bounce. It didn't fly as far off to the side compared to our hot puck. And that's why they keep these pucks on ice throughout the game. They'd much rather have a puck that's going to glide, that's going to see reduced friction, compared to a puck that's going to be bouncing around everywhere. It's just much more difficult to handle a puck that's bouncing everywhere, right? Now, the next thing I want to talk about, one of my favorite things, is probably the thing that I'm worst at when I actually play hockey, but it's a slap shot. So, the slap shot is the hardest, or at least the most powerful shot you can do in hockey. And there's a couple things that really kind of play into that, right? So, you've got kinetic energy. Kinetic energy is the energy that is from motion, right? So, you've got kinetic energy, you've got potential energy, which potential energy is that energy before something's in motion. So it's that all that energy that could be converted to that could be kinetic energy is potential energy before it becomes that. And then another piece of energy that you have, especially with a slap shot, is elastic energy. And elastic energy is basically like if you had a rubber band, right? It's something that stretches, and then when you let go of that stretch, it flings back. That's that amount of energy. And it's kind of a combination of all of these things. And all of these go into the work, the amount of work that is put into our puck when we shoot it. And every hockey stick, let me flip this over so you can see it a little better. Every hockey stick has a flex number, right? And it might be flipped backwards, but basically this flex, typically between like 70 and like 110 or so, is the amount of weight, the amount of pressure that's required to bend the stick 1 inch, for that stick to flex 1 inch. The higher that number is, the more weight's going to be required to bend that stick, which means it's going to take a lot more effort to get more elastic energy, but you'll be able to put more kinetic energy into it. And when you're hitting a slap shot, you don't want to hit the puck directly as you come down. You hit the ice first, and actually the stick will bend, building up that elastic energy. And the combination of the power behind your swing, as well as that elastic energy that's built up, once it hits the puck, that's what gives it all of the energy. So to put this in perspective, some of the best shooters, the most powerful shooters in hockey can shoot a slap shot about 100 miles an hour, just over 100 miles an hour. That's essentially producing about 77 kilowatts of energy. That's how much energy is going into that slap shot. And they can go a little bit more, a little bit less, depending on the shot. But a lot of that is determined by the flex on your stick. So when you're shooting, like I said before, you want to hit the ground first rather than just hit the puck. Because with just the puck, all you get is the kinetic energy being converted, but you're not maximizing your energy conversion. If you hit first, you get a lot more power into it, like you can see right there, right? So just hitting the puck, it's less power. But if you hit first, you can even hear it. It sounds a little bit louder. And that conversion right there is the key to a slap shot. So if you're ever taking a slap shot while you're playing hockey, you always want to make sure that your stick is hitting just before the puck compared to trying to hit the puck only. That's also going to be how you do like a lot of what I do when I play hockey and just completely miss the puck when you try to slap shot. I'm really bad at that. I'm good at skating, less good at the stick play. But that's kind of the secret behind that, is you want to make sure that you're getting the elastic energy, converting this potential energy right here, the potential energy, kinetic energy, elastic energy, all the way into the shot right there. And that's that full conversion to make an effective shot. And the curvature of your stick is also going to help determine how much elevation, how easy it's going to be able to get the elevation. If you have a flatter stick, the puck, when it hits this, is going to roll straight across, and it's not really going to get as much lift compared to if you have more of a curve. It'll roll up. You'll be able to get a little more lift on the end and fling it higher. So that's going to be how you score like your top shelf goals, or you're going to dump the puck out into the other zone, or different stuff like that. And the last thing I want to talk about here, the last little thing, is going to be the physics of checking. Something that I was always really good at because I was a big dude. Hitting other players in hockey, that is something that is, kind of what it's known for, and it's fun. And the science behind it is, you typically, if you're thinking about it, right, you'd think the bigger guy would probably be better at taking somebody down, right? If a bigger guy is hitting a smaller guy, the smaller guy is going to lose, right? But that's not necessarily what goes into it. There's a lot of different things that go into it. It's leverage, it's speed, there's lots of different factors that actually go into a check, right? It's weight. So what I've got right here is this little course, and I'm going to lower the camera so we can see it a bit better. But basically what this is, and what I'm going to do, is we have a couple players here. Now these players are going to be these fancy balls, and each of these balls has a different size, different weight, different density, all of these things that go into not communication, but collisions between players, right? And this right here is going to be our player that's getting checked. It's going to be, he's not that big, right, compared to some of these other balls. In terms of size, he's not that big, but he's a little more dense. He's got a better kind of center of gravity there. So we're going to put him right here on this X. And what we're going to do is we're going to see how far certain players will be able to move this ball depending on their speed and size and everything by rolling them down this ramp. So we'll start off with the biggest player I've got in here, right? This is Earth. Pretty big. But he's really not that heavy. So let's see how far he can move this ball. Didn't even really budge, right? So that kind of shows that just the actual size isn't everything. Let's try this. Another one. It's a little bit bigger than our ball, but very, very light. And let's see what happens. Literally nothing. Perfect. Now, same thing here. Another ball, fairly light. Let's see what happens. Nothing. Now we're going to try this. We've got a baseball. So a little bit bigger. Honestly, a fairly similar size. So let's see what happens here. So it moved it a little bit more, but you'll see that it's not just the size that impacts it, right? It's the speed, it's the actual density. The density is a really, really big one. The density and the center of gravity are really, really huge when it comes to checking, right? So we're going to switch this around, and we're going to make this guy the one that's making the hit. So let's see how far this little guy can move our Earth. Oh yeah, he just pushed him all the way down there. He just completely cleared him out on that forecheck. All right, so we're gonna move the Earth here. Let's see what else. We got a baseball. Now let's see how far this guy will move the baseball. Again, big hit. So this guy's a big hitter right here. I like this guy. I would want him on my team. All right, we're gonna try one more. I think you guys kind of get the general idea of this. We're gonna try this little ball. Ready? Oh yeah, he pushed him all the way down the ice. So when it comes to checking, when it comes to making these hits, right? I'm going to adjust this. When it comes to making these hits, it's not just size that goes into this. So you can be any size and still play hockey and still have fun and still be effective, depending on your leverage, depending on your speed, depending on the size and everything there. You can really kind of incorporate all of that into how you play. So that is the last little bit of demo I had for you. I just love hockey, and I love talking hockey, and I love playing hockey. So any excuse I can have to talk hockey with you guys and kind of teach you a little bit more about some of the science behind it, I'm going to take it. So I hope you guys all enjoyed this. I had a lot of fun. Have a great rest of your day, guys, and thank you so much for watching all of our videos. If you want to see more, you can go ahead to go to azscience.org or follow us on Facebook and Instagram for all of our different video content. Thank you guys so much. Have a great day.